This all dealt with Thomson's charge to mass ratio experiment, and ultimately, I mean, there's more involved than just this, but ultimately in the production of cathode rays, which is just a stream of electrons, I still haven't told you why they produce green light, but we'll get to that eventually. You have, in his experiment, you have this region where you have overlapping electric and magnetic fields. That's in the middle of your screen right now. And your analysis starts by saying that the forces on the beam or the forces on the particle in the beam are balanced, which means you say that the magnitude of the electric force and the magnitude of the magnetic force are equal. I admit I got a little bit lazy in typing this up. I do have magnitude of the force equals magnitude of the force, but I probably should have a vector symbol and absolute value signs to really highlight that. On the other hand, the second part of his experiment allows the beam of what we now know are electrons to enter a magnetic field where they travel in a circular arc, in which case your starting point is to say there's a net force that's equal to the magnetic force, and you would be perfectly within your rights to put vector symbols above those because they are the same force. It's not two different forces. You can analyze that using the skills that we learned and the formulas that we learned in Unit 2. If Fm equals Fe, then you can write QVB equals QE, and you can go from there and find whatever it is you're asked to find. If Fnet equals Fm, then you can write Ma, which is Fnet, equals QVB, which is the magnetic net force. The acceleration is centripetal. So you change the acceleration to v squared over r, and you end up with mv equals qbr, which I don't have written. But if we cancel one of the v's and multiply by r, you get mv equals qbr. And you use that to find whatever you need to find. And lastly, although Thomson couldn't do this, you know, in the acceleration or production of the cathode rays, you could use conservation of energy. So all that being said, does anybody have any questions here you would like me to go over? Go ahead, Willis. Certainly. So we have a negatively charged particle. I don't know how helpful that is. We're given the mass of the particle. We're given how fast the particle is moving, and it moves through a magnetic field. And then you're given the radius, and you're asked for how many electrons the particle carries. Can I ask you a question, Willis? Had this question just said, what is the charge on the particle, would you have been able to do it, do you think? Probably. Okay. So it's just that added layer. We're going to start off with the big picture, which is that you have a magnetic force that's the net force acting on a particle, which means that the net force has a magnitude equal to the magnetic force. I will be more specific here. You don't need to do that. This becomes Ma equals QVB. The acceleration is centripetal, and now you can go to your formula sheet and see that acceleration that's centripetal is v squared over r. So we get mv squared over r equals QVB. If we cross multiply here, you get mv squared equals q times v times b times r. And we have a v on both sides that can cancel. So this is why I said you get mv equals qbr. And it doesn't say what is the charge. It says how many extra electrons are on it. That negative, that piece of information that the charge is negative turns out to be important. Why is a particle charged negative? Why does an object carry a negative charge? It's because it has extra electrons. Unless it is an electron, in which case it's negative because it's an electron. But if I have a bundle of matter that carries a negative charge, that's because it has extra electrons. And this is going to be very important for today, actually. Just to show you something that I'm going to refer to today in today's lesson, these are allowable charges, these numbers. There's no need to write this down. Objects are allowed to have, let's just assume these are all negative. Objects are allowed to have that charge on the top because they would have one extra electron. Objects are allowed to have that charge because that corresponds to 2 electron charges. The bottom line, everybody, is the charge that an object has is always a whole number times the elementary charge. So going back to our problem here, if I can determine the charge by taking mv over br, and I'm not going to do the calculations. I'm going to tell you that what you are going to get when you do this is something very close to 4.8 times 10 to the negative 19. I don't know what you get exactly. Maybe you get 4.75 times 10 to the negative 19. Does anybody have the number? It works out almost exactly to 4.8? Oh, sorry. 4.8. So it does work out to 4.8. 4.8 times 10 to the negative 19. And that's coulombs. So if you want to determine how many electrons are responsible for that charge, very similar to what we just did with the photons in the exam question, many of us will know that you take this charge that's written on the board and divide by the charge on one electron to get how many electrons, and you're going to get 3. And that's the answer. But some of us, that may not be obvious. And in the heat of an exam, it's very easy to forget things. It's very easy to forget things at the best of times. So a ratio is a tried and true mathematical method that you can use to find how many objects make up a bundle of them. And we could use that ratio and solve for x. Is that okay, Willis? Okay, any other questions? Go ahead, Farhan. 17? Certainly. So we have a beam of electrons traveling with a particular speed. Now, I think I know what this question is about. I'm not going to go through and do all of the calculations, but I'm going to explain how we would find the answers, okay? And it's moving at 2.5 times 10 to the 6 meters per second. We've got a magnetic field. The magnetic field is oriented into the plane of the paper. These are electrons, so if you were to use the right-hand rule, you would determine the force due to the magnetic field on the electrons is towards the bottom of the page. So whenever you have an electron moving immediately when it enters this field, it will be forced down due to magnetic effects. On the other hand, if you take a look at the polarity of the potential difference, the positive terminal is on the top, and that's connected directly to the plate on the top. So the electric force is towards the top of the page, the magnetic force is towards the bottom. You're asked to determine the magnitude of the instantaneous acceleration when they first enter the region between the plates. Acceleration is found by relating the net force to the acceleration with Newton's second law of motion. The net force will be equal to the mass times the acceleration. You cannot find an acceleration of a particle in terms of forces unless you consider all of the forces acting on the particle. You can't just look at one of the forces, you have to look at them all, because they all influence the behavior of the motion of the particle. So these two forces are in opposite directions, Farhan. What that means is we're going to have to subtract the two forces, but we're going to have to know which one is bigger, because when you subtract two forces to find the net force for opposite forces, you always have to have bigger minus smaller. So what you would have to do here is calculate Q times the electric field, and you would get a certain number of newtons, and it would be up. And then you're going to calculate Q times V times B, which is how we find the magnetic force, and that's going to be so many newtons, but it will be down. One of these two forces will be bigger. Well, maybe not. Maybe they're exactly the same number. If they happen to exactly be the same number, then the answer to this question would be 0. Once we take the larger of the two forces, Farhan, and subtract the smaller, then you can set that equal to MA. And if you want to be kind of crafty about it, you could do this. This has nothing to do with magnitudes of forces. I'm just saying, do we really need to know which one is bigger? Well, not really. I guess if we wanted to know the direction of the net force, we would. But just subtract the two forces, and if you get a negative, forget about the negative because you subtract them the wrong way. Anyway, once you find that net force, you can divide by the mass to get the acceleration. Does that make sense? Okay. We don't have a very long lesson today, and I understand that there will probably be more questions, but I don't want to spend any more time really right now going over these questions, because then I'm going to be rushing to get through the lesson. If we have more time after the lesson and you have more individual questions, I'd be happy to come around and help you. So we are looking now at lesson 30.4.2, which is called Millikan's oil drop experiment. What I think is the nice thing about this lesson is the same as the thing that was nice about the last lesson. There's really no new physics. It's just an application of physics that you're already familiar with. Millikan is a fellow who investigated the photoelectric effect. All of those experiments that we talked about with the photoelectric effect were done primarily by Millikan in the early stages of the study of this kind of physics. Millikan's also the person responsible for determining the elementary charge. So when you look at your formula sheet and you see the elementary charge, or the charge of an electron, is 1.60 times 10 to the negative 19 coulombs, this is the person who figured out how to determine it, which is an amazing feat. You know, you think about how would you even begin to determine the charge on a particle so small? The answer is, it's accomplished by doing a force analysis. In fact, the force analysis that we're going to do here in Millikan's oil drop experiment is pretty much the same type of force analysis we did when we answered question 17 a minute ago. We're going to be looking at balancing forces primarily. So once Thomson discovered the electron, Millikan determined the charge of the electron. So I want to pause for a second here. One of the things I didn't review from last Thursday is that Thomson determined the charge to mass ratio of an electron, and I believe it's, I'm pretty sure this is right, approximately 1.76 times 10 to the 11 coulombs per kilogram. And that number was thrown out in the last lesson. So when you think about this, if Millikan is able to determine the charge of the electron, then Millikan also determines the mass of the electron. Because once you know the charge, you can put the charge here. For those of you watching video, you can put the charge here that Millikan determines, and then you can use this relationship to find the mass. So he's credited with determining the charge, but really a secondary aspect of this experiment is he will now know the mass. Just to review here, you know the elementary charge, which is the charge on a single electron, is given the symbol E, lowercase e, and it has a value of 1.60 times 10 to the negative 19. It's the elementary charge because it's the smallest unit of charge. And although at the end of this unit I'm going to tell you that what I'm going to say next is a lie, for the time being we have to understand what that means is that charge always comes in multiples of that number. And that's a lie. Okay, later on I'm going to tell you that's not true. There's exceptions to that. But when you talk about charging pith balls or charging little droplets of oil, which is what he uses in his experiment, these charges are all allowable because they happen to be an exact multiple of the elementary charge. Whereas things like these charges are not allowable. If you were to take 1.3 times 10 to the negative 19 coulombs and divide by the elementary charge, which we know, Millikan didn't know, it gets 0.81 of an electron. If you do the same for these other ones, you get non-integral numbers, is what we would say in science. You get a decimal number of electrons. And this forms the whole basis for his experiment. In fact, I'll tell you what he does, then we'll get into the nuts and bolts of it. He somehow charges little tiny microscopic droplets of oil, like machine oil, sewing machine oil, engine oil, sprayed into a fine mist, and you charge the drops. Okay? And then what he does is somehow he determines the charge on this drop, and he writes it down. And then he picks a different drop, and he determines the charge on that drop, and he writes it down. And he does this for thousands of drops over a number of years. And what he discovers is the charges you get for any oil drop always fall into the column on the left. Now, he doesn't know the elementary charge, but he's smart enough mathematically to recognize that there's a factor that's common to all of these, 1.6 times 10 to the negative 19 coulombs. He never, ever gets, for the charge on one of these drops of oil, a number that's not a multiple of 1.6 times 10 to the negative 19. Which means he doesn't really measure the charge of an electron, he determines the charge of an electron. He never measures it. All right, so here's his apparatus. This is from your textbook, if you ever look at your textbook. It contains a vacuum chamber, so this whole unit is sealed off. This hole in the back that you're looking at, I'm guessing it would be connected to a vacuum pump where you would pump all of the air out. He's going to spray in some oil. We'll talk in a second about what the atomizer does. But there's going to be a fine mist of oil that's sprayed into this apparatus above a top plate that has a little tiny hole in it. And as a result, gravity pulls those drops down, and some of the drops fall through the hole. They fall very slowly. Once he's got drops in there, he has to look at them under a microscope. So he looks through the lens of the microscope. And when you actually do this, it's a really frustrating lab to do. I did it in university, and I tried doing it in high school in my first or second year of teaching. It's a mess. It's very difficult. You look through the eyepiece while you shine a light in there, and you're in total darkness. Okay, you're in total darkness. So maybe you're looking this way, and you're shining a light through a hole in the front of this, and the light is coming at right angles to what you're looking at. And the light reflects or bounces off of the little oil drops. And you're in a totally darkened room. You even have this really thick black felt blanket over top of you, and you're under there looking there. And it's actually pretty cool if you get a chance to do this. You look in there, and it looks like you're looking at the stars. It looks like you're looking at the nighttime sky, and you see all these stars, except they're moving around. Some of them are moving to the right, some of them are moving to the left, some are going up, some are going down. The atomizer is simply, there are two types of ways to deliver perfume. You can have a pump bottle, which just basically drives liquid up through a tiny opening, and the opening takes the liquid and spreads it out. Or you can use an atomizer. How many of you have seen perfume bottles with a squeeze bulb? Okay. They're called atomizers, and what they do is they blow air over the surface of the perfume, and they don't draw the liquid up, they just blow the top air molecules off, or the top perfume molecules off. It's a very, very fine mist that it creates. There's a potential difference between these plates, and it's variable. So that's kind of the setup. Millikan sprays a fine mist of oil drops into the area between the two plates. The drops are charged. Now, first of all, my whole explanation of this experiment is vastly oversimplified. Okay? What we typically say in high school physics is they're charged through friction with the air when they leave the atomizer. And some of them become positively charged and some of them become negatively charged. In reality, you probably spray them in there and then you hit the apparatus with a blast of X-ray radiation, which is ionizing radiation, which will pop electrons off of some of these particles, making them positive. But to make things simple here, what we say is that some of the particles could be positive and some could be negative. We're interested at this level in the physics analysis, not in the history of the experiment. And what Millikan does is he looks through the microscope, he picks an oil drop, and he adjusts the voltage until it's stationary. No, wait a minute. First of all, why would a drop be falling when it's in between the two plates? It's a very open-ended question. And there's a number of answers. Evan? Because there's a force of gravity. If the force of gravity were the only force acting on the drop, what would the acceleration of the drop be? Be 9.81. And there's the first kind of lie, because there's a lot of air resistance that we would have to take into account if we were in university. But it would accelerate at 9.81 here in this classroom. Okay, I'm going to jump ahead a bit here. Could the drop be accelerating down when it's in between the two plates? Oh, by the way, if it's accelerating down at 9.81, what's the voltage between the plates? So it would be 0 because there's no electric force. Could the drop be accelerating down at like 5 meters per second squared? Could, but that would mean there's an electric force up opposing the gravitational force. If the drop were accelerating down at 5 meters per second squared, which of those two forces would be greater? There's an electric force and there's a gravitational force. The electric force is up, the gravitational force is down, but it's only accelerating at 5 meters per second squared, not 9.81. Which is up and which is down? No? That's right. The electric force would be up, but it would be smaller than the force of gravity downward. So this is what we mean when we say a force analysis. If he adjusts the voltage so that one drop is suspended, he's creating an electric force acting on that particular drop, which is exactly balanced by the force of gravity. So if a drop is falling and he increases the voltage, then it should start falling at a less rate until it finally stops falling. This is very tricky. I'm going to ask a question outside of this little lecture right now. What would be going on if you had a drop that was falling and he increased the voltage and it fell, quote, faster? It started accelerating even more. Why would that happen? Ben? Right, which would mean if the bottom plate is negative, that drop is positive. But Millikan's smart. He's got a little button on here that you hit and it switches the polarity of the plates. Okay. Bottom line is, there's his original apparatus. I guess this is the vacuum tube here coming out. There's the atomizer, so this is filled with some kind of machine oil. There's the microscope. I'm guessing that probably the light source would be in here. You don't want the light source coming right at your eyes, right? So the light would be entering there, reflecting off of the oil drops to his eyes. Here's a more modern one, well, commercially manufactured one. And here is one, this is probably the same one that I tried using for teaching this in high school one time. It just doesn't work. It's a piece of garbage. I shouldn't say that. It's very difficult to learn from, is how I would put it. So, since a particular drop was suspended, the forces acting on the drop must be balanced, and the magnitude of the electric force and the magnitude of the gravitational force have to be equal. So how is Millikan able to determine the charge on the drop? I've crossed off measured because measured sounds like he's measuring it directly. He's not. He's determining the charge on the drop by measuring other things. Well, It's very simple, actually. You don't need to draw this apparatus. I just have it up here. There's a drop. If it's suspended, when you look at the drop, you'll recognize it's suspended. It's not moving. There's a force of gravity acting down because the drop has mass. There must be an electric force acting up because there has to be some balancing force. And it's not magnetic because there's no magnets. It's electric because there are charged plates. This is the analysis. When we did number 17 and I said, let's calculate Fe and calculate Fm, if they were in opposite directions and the beam was balanced, then we would set them equal to each other. How do we calculate the electric force? It's charge times electric field. How do we calculate magnetic force? Well, mass times gravitational field. This is all, the formula on the right is from Science 10, really, and the formula on the left is from Unit 2 here in this course. Just test you here. How many of you remember how to calculate the electric field strength in a situation like this? Evan? Right, voltage over distance between the plates. So there's the answer to the question. The answer to the question is you can now measure the voltage, you can measure the distance between the plates. You know, he hooks a voltmeter up, 12 volts. He takes a ruler and he puts it there, 1.58 centimeters. He knows 9.81 is G. Now the problem is, how does he determine the mass? That's a difficult question. That's an incredibly difficult question. And what we teach you in high school physics is not how you would probably really do it. You really do it by looking at things like terminal velocity and friction with air. But for some reason, the powers that be say in high school, we have to teach it to you this way. What he does is he measures the size of the drop. He looks through the telescope. I know. He looks through the telescope, and on the back, behind the drop that he's looking at, there is a ruler. Okay? It's a microscopic ruler that's been manufactured, and this does work, by the way, but it's not how he did it. It's been manufactured under a microscope, and you could do this if you had a microscope. You take a ruler and a lot of patience, and you mark off 2 lines that are 1 millimeter apart. And then you blow it up so the field of vision on your calculator makes it look bigger between them. And did I say on your calculator? Under the microscope, the field of vision makes the distance between those 2 lines bigger, and you take a very fine marking device and you put it as close to between those lines as you can, and you put another mark. And you've put a mark at 0.5 millimeter. And then you blow it up and you keep repeating the process. It's possible to construct a ruler you can see under a microscope. If he knows the diameter of the drop, he can calculate the volume of the drop. And if he knows the density of the oil, he can use the volume to find the mass. All density is how many kilograms per cubic meter. So if I want to know the density of oil, I wouldn't use a whole cubic meter. I'd make it smaller. But I could take a box that's 1 meter by 1 meter by 1 meter, put it on a weigh scale, something that would measure kilograms, zero the scale, fill it with oil, and read how many kilograms are in that cubic meter. It's just a ratio. So if you determine how many cubic meters the drop is, we're back to setting up a ratio. You're going to end up saying that the density, which is how many kilograms, a certain number of kilograms is 1 cubic meter. Then you're going to have the mass of the drop over the volume of the drop. One of the examples we look at today will make use of the density formula. So, first point here, and I already really said this, if he repeats this experiment hundreds and hundreds and hundreds of times, what he discovered is that each drop always consisted of a multiple of the elementary charge for a charge. He didn't know the elementary charge. So if I gave you 1,000 different charges that were all a multiple of that number, mathematically it's a puzzle to try to figure out what that thing is that everything is a multiple of. But he was able to do it. And that's true. That's not a jazzed up version for high school. So every charge he ever determined was always a multiple of that. That's how we know the charge of an electron. That's how we initially knew it. So example 1, if we have an oil drop with a particular mass and it's suspended when the distance between the plates is 0.95 centimeters, if the voltage is 340 volts, then it's suspended. What's the charge in the drop? And how many excess electrons, which is kind of Willis's question from the beginning of the class. If we can determine the charge, we can figure out how many electrons there are. So we start off by saying the magnitude of the electric force, the magnitude of the gravitational force are equal. This becomes Q times electric field strength. This becomes M times G. So this becomes Q V over D equals mg. This is what I meant when I started off this lesson by saying there's no new physics here. All we're doing is applying physics to a new situation. I'm a rearranger. I don't like to put things in and then rearrange, so I would rearrange this and write Q delta V equals mgd. I think you know this about me. I tend to drop that delta on the D. I don't think it's really important. It's the distance between the plates, which means that the charge is mgd over the voltage. And, quite frankly, I'm not going to write down the numbers. If you want to write the numbers down on your handout, you can. But I don't think it's really necessary. We've got all the numbers right there in the question. All we have to do is put them into our calculator. So mgd over voltage, the mass is 3.5 multiplied by 10 to the negative 15 times g, which is 9.81, times the distance between the plates. You always want to use standard units unless I've given you an out. Unless I've described to you a situation where you can't, like the 1242 thing. We don't need standard units. And then I have to divide by the voltage, which is 340 volts. Just double check my entries here. I think it looks okay. So I get this for a charge, roughly 9.59. Times 10 to the negative 19. Yep. 19 coulombs. The number of electrons. Now, Millikan wouldn't have done this next step. Millikan would have just stopped at that point, recorded in his lab result journal the charge on the drop I studied this afternoon had this value. But we know what the elementary charge is. So one way or another, I want you to calculate how many extra electrons that object had. You can use a ratio. You can just use common sense. I believe the number is going to be 6. So you get 6 electrons. And all I'm doing is I'm dividing this charge by the elementary charge. Now, in reality, would it have been a negatively charged drop? Yeah, because the top plate's positive and the electric force was up. Go ahead, Farhan.
Okay, so Millikan is determining the charge on the droplet of oil, but that has multiple electrons.
Yes.
So he's determining the mass for the droplet of oil, which is going to be more than an electron, obviously. So after he found after doing this 1,000 times, finding the 1.6 times 10 to the negative 19, would he just put that in the original formula to find the mass of the electron?
We'll get to that later. Okay, that's just a little ahead of us, and I don't want to worry about that. All he would do is he would use the charge to mass ratio to find the mass. Go ahead.
Just kind of with this experiment, it's the electric force and electric force and
This is what we're ignoring. And it's a big fat lie. So when we say, oh, if don't forget your question, Liam. If we say, oh, well, if the plates are turned off, it's going to accelerate down at 9.81 meters per second squared, that's a big fat lie. That's like dropping a balloon filled with air and expecting it to fall at 9.81. So the analysis that is the true analysis that takes into account air resistance is too complicated for this level. So we make it simple and we say we're going to assume no friction with air, which is, I mean, if I drop a baseball, I can assume no friction with air. We always see that in physics 20, right? Assume no friction with air, assume negligible air resistance. When you're talking about tiny, tiny particles with little mass, the resistance with air becomes significant. So, and this is an issue I have with teaching this, is I am lying to you. But the diploma exam will as well. So the diploma exam manager told me one time years ago that they try to choose masses of drops that would make the air resistance really negligible. And I kind of think it's not going to become really negligible until you get to like 10 grams. In which case you don't need a microscope to see that. It's a big blob of oil. I don't know if you're satisfied with that answer or not.
But I mean, if the two forces are equal, would air resistance not exist then? Because then electron, or the oil would not be traveling at all.
It would be stationary. Yes. I'm not getting your point, but I want to make sure you get my point first. Okay. If this were university and you did the force analysis, we actually call the air resistance force a buoyant force. It's like having something underwater. There's a buoyant force upwards which makes it feel lighter. You know that. Even though under the right circumstances, if you held your breath and controlled your breathing, you can sink in water. And under other circumstances, you can float. But if you sink in water and you're walking along the bottom of the water, you do not weigh as much. There's a buoyant force up. So in reality, when you do this analysis, if you were to do it, your analysis would be that if the drop is truly stationary, that there is a force of gravity downwards that is balanced by two forces upward. The force of buoyancy and the electric force. Are you satisfied with that now? Okay, so we managed to connect there. Go ahead, Liam.
I was just going to say the other number for the transfer. It's supposed to be 9.59 instead of negative 19 or 1.5.
Oh, did I? Oh, thank you. Oh, look at that. 9.59? Okay, I'll just use a different color to make sure that you see my mistake. It should be 9.59 times 10 to the negative 19. And you get 6 electrons. Okay. So, this is the bad thing about this discussion, is I think it's an important discussion to have because some of you will go on and take post-secondary physics. But in the process, I hope I'm not confusing anybody by talking about this. The bottom line is, everybody, if it's stationary, at this level, this is what we say, even though it's not really true. It's one of the only places in this course where I have to do that. I have to teach something that's false. Yeah. Go ahead.
So because the vacuum container is under a vacuum, the pressure in the vacuum has something to do with buoyancy?
You'll never get a perfect vacuum. That's another way that we can justify it in high school, is if you could get a perfect vacuum, then air resistance is negligible. But let's go with that. Let's go with that since it's in a vacuum, those forces are the true forces. But, and now we're getting into more of the university thing, that whole deal of how he finds the mass is not how he finds the mass. He lets air into the region and measures the terminal velocity of the drop. And there's a relationship you understand what terminal velocity means? If I jump out of an airplane to go skydiving, I'm going to accelerate, accelerate, accelerate. But then at around 27 or 28 meters per second squared, meters per second rather, depending on how I shape my body, I level out at a particular speed. That's the terminal velocity. There's a relationship between the terminal velocity of a falling object and the mass of the object and the size of the object and the temperature of the air it's falling through and all of these things. So he definitely makes use of the buoyant force. Sorry, I'm distracted right now. I'm wondering if I have that here. I don't. He definitely makes use of the buoyant force to find the mass. And I'm just wondering, I have my lab book from university where I did this lab. It's probably at home. I'll see if I can remember to bring it in. And I'm sure we did this analysis. And maybe that's because the apparatus we had, we didn't have access to a vacuum that could remove all the air. I don't know. You were right, though. If you could get a perfect vacuum, if you could pump all of that air out, then the buoyant force wouldn't exist because it's a product of the interaction of the air with the drop, which would mean the two forces would actually only be electric and magnetic, or electric and gravitational. Does that answer your question? Okay. Any other questions before we go on? Okay, so then we have to talk about what if the drop is not suspended. Now this first situation really throws people. I tell you the drop is moving up at a constant speed of 2 meters per second. It doesn't matter how fast it's moving. If it's moving up at a constant speed, its acceleration is 0. The physics analysis of a drop moving up or down at a constant speed is no different than the physics analysis of a drop that's suspended. Because both of those situations have 0 acceleration. And if they have 0 acceleration, they have, if you look up here on the board, the net force is equal to 0. If you're watching this video, you can't see what I'm pointing at. You know, uniform motion, constant velocity, motion at a constant speed in a straight line. The net force is 0, so the acceleration is 0. If the net force is 0, the forces are balanced. Well, if the forces are balanced, then this is the analysis. This is your starting point. I'm not going to write down the rest of this. You would, of course, change this to QE equals mg, but you could go from there. This opens the door. This is the big picture that we always talk about. What if it was accelerating up? Okay, there is only one possible way, assuming the only two forces are electric and gravitational. There is only one possible way for the drop to accelerate up, and that's because there's an electric force up that's greater than the gravitational force down. In which case, if I said to you, how do you find the net force? You'd say, well, I take the bigger force minus the smaller force. And we would end up with, so this is not uniform motion. This is actually linear acceleration. Because the net force is not 0. The net force would be equal to Fe minus Fg. What does that mean? Where would you go from there? What you would do is this. If you had a problem where you identified that this is the situation, we could write Ma equals QE minus mg. And of course, you're not going to confuse g, which is the acceleration due to gravity, with A, which is the acceleration that the drop is experiencing. What if it's accelerating down? Well, we actually talked about this. If it's accelerating down, it could be accelerating down really fast. Like, it could be accelerating down at 12 meters per second squared. And if it is accelerating down, assuming these are the only two forces, it is accelerating down at a value that's larger in a negative direction than 9.81, then the electric force must also be down. This again is a situation where we have linear acceleration. And where you would go from here is, since you're going to add those two forces together, this would be MA equals QE plus mg. I want to just take a little side note. And we're going to encounter this, I think, on an assignment I'm going to give you later this week or early next week. It is possible, looking at this diagram that I have on the board right now, for you to tell me very close to the correct value of the acceleration of this drop. You should be able to tell me how many meters per second squared this drop will be accelerating down. Not knowing anything else, just looking at that diagram. Does anybody have a number? Liam's got one. I'm going to give everybody else a minute here to maybe think about it. Does anybody else have a number? No? Liam, you want to? About 18, I can live with that. 18 meters per second squared. Did you happen to see what I had up there before I erased it? Okay. Why? So I'm going to pause there and say to everybody else what you just said to me. That the length of the vector for the electric force, you said, is about 0.8 times the length of the vector for the gravitational. So I'm just going to say 80%, same thing. And we know that the gravitational force results in about, oh heck, I'm not even going to say 9.8. I'm going to say that the gravitational force always has to account for about 10 meters per second squared. I think if you had me for Physics 20, you probably remember me saying sometimes, well, it's 10. 9.81, it's 10. Let's just call it 10 just for the sake of explanation. So if that amount of newtons that's indicated by the length of the gravitational force would be responsible for about 10 meters per second squared, and the electric force appears to be about 80% the size of the gravitational force, 80% of 10 is about 8 meters per second squared. Well, it's not about, it is 8 meters per second squared. So if the force on the right produces 10 meters per second squared of acceleration downward, and the force on the left is about 80% of that, it would produce 8. Well, we get 18. What if the drop is accelerating down less than 9.81? So just take a look at these two vectors and convince yourself that it will, first of all, accelerate down. And it has to be less than 9.81. Downward. Okay, it's going to accelerate down because the gravitational force is greater. So we have unbalanced forces. Get this out of the way first. The net force will be equal to the gravitational minus the electric, which would mean MA equals mg minus QE. Take a look at what I've written here and what I've written for number 2, I believe. Do you see that they're the same, but you subtract in the opposite order? When I was in maybe junior high, I discovered that if I subtracted the wrong way and I'd get a negative, I'd just forget about the negative and say that's my answer. That won't work here. It's more complicated than that because there's that third term. Okay. I want everybody to see if you can figure out how many meters per second squared downward this drop would accelerate. How would you determine the acceleration of the drop in example 1 if the voltage between the plates was changed? And I need your help here. Was it 340 volts? Okay, so it was 340 volts. And at 340 volts, the drop was suspended. If it's suspended at 340 volts, what's going to happen to the drop if we increase that voltage to 375? It's going to start accelerating up, isn't it? Because increasing the voltage will increase the electric force. And right now at 340, the two forces are equal. So if I increase the electric force, it's going to be a greater force upward. It's going to accelerate up, which would mean that the net force would be equal to the electric force minus the force of gravity, because the electric force is the bigger force, upwards. We're not going to calculate this. It just says show how we would do it. If you now go back to when it was 340 volts and it's balanced, if I decrease the voltage to 300, that's going to shrink the electric force, making the electric force smaller than the required force to balance the drop, which means it's going to accelerate down, which means the gravitational force will be bigger than the electric force. So we subtract them in this order. Does that make sense? Okay. One final example. Example 3 gives you a lot of information. It gives you the same information that we had in example 1, basically, and asks us to find the charge on the drop. The drop is suspended, so you're going to have the electric force, QE, equals the gravitational force, mg, and you can calculate the electric field strength by going voltage over distance between the plates. And you can use that to find the charge. Okay? The difference is in this question, you don't know the mass. Right? You don't know the mass. You're told, however, the diameter is 3.18 times 10 to the negative 6 meters. And you might ask why we're not given the radius, but you're given the diameter. When you measure the size of a sphere, you can't measure the radius directly. I mean, if I gave you a basketball and I said, what's the radius? You can't put your ruler from the center to the outside. It's impossible. But you can put your ruler up against it and measure the diameter and then divide by 2 to get the radius. The density of the drop is given here. And we can find the volume of the drop using 4/3 pi r cubed. Is that on your formula sheet? Under the math portion? It's not. I didn't think so. I would say that if you were ever given a problem where you had to use this method to find the mass, you would be given that formula as part of the question. I would certainly give it to you. So the first thing I would like everybody to do is calculate the volume. You're going to have to take the diameter and divide it by 2 before you use the volume formula, because the volume formula is for radius.